Okay, we're going to look at internal energy today. Internal energy is the energy due to the kinetic and potential energy of the particles in the system. So does the ice water or an equal quantity of hot chocolate have greater internal energy? Jacob says hot chocolate. You guys.
That way the microphone can hear you.
Hot chocolate. Wait, how thick is the hot chocolate?
Which has more internal energy, a gallon of cold water or a drop of hot chocolate? Ooh.
Gallon.
What type of hot chocolate?
Yeah, is it milk or water based?
How would you determine that? What's it based on?
Meter particles. Potential energy and kinetic
And how many particles there are.
Dang it.
Right? Look at the gallon versus a drop. The hot chocolate has more energy, but there's a lot more. Tricky. I don't know. We'll see.
What's the drop?
We'll see.
Depends what the difference is.
Depends on the temperature difference.
Which country?
You would probably need some numbers with that one, right? What will the internal energy of the water and hot chocolate change over time?
They'll equal 100.
They'll end up what? They'll end up being equal to each other. This one, what will happen to the water? And warm up, and this one will cool down to room temperature. Yeah.
Is that a marshmallow?
Yeah, but the marshmallow will change the. Yeah.
So internal energy is represented by letter U, and it's the energy contained within the particles of a substance. And heat is represented by the letter Q. It's the internal energy transferred between objects. So heat always moves from high temperature to low temperature, and the rate of transfer depends on the difference in temperature. So if you touch something really hot, the heat is transferring really fast, which is why it feels really hot. Yeah.
One of the kids today asked, what does NRG stand for? It's second semester. What did he say?
So the greater the temperature difference, the greater the rate of energy transfer. So which way does the heat flow if you place a warm canned beverage and cold water?
Why would you have a warm can beverage?
We're trying to cool it down by putting it in cold water, Sam.
Like cold ice water?
Yeah.
Like in a cooler?
The heat from the can will go to
Yeah. So the heat from the can goes to the water. So how does this occur on a molecular level? Let's look. The collisions of this is the water molecules are slower. The can is faster because it's warmer. And they're going to transfer some of their energy to the cold can. And it will transfer the energy from these particles will get transferred to water. Oh, I guess right here, I was wondering. That's the can, the metal can. So it transfers it to the metal can, they transfer it out to the water molecules. And yes, metals are very good conductors.
What type of metal is that? Do you think that metal was aluminum or plutonium?
Okay, let's try this. I need to make sure my speakers get...
What is with all the tabs?
Okay, the first ones, I have to make stuff for my son's birthday party, so I have, like, recipes up.
What game are you playing at the birthday party?
No game.
What? You don't have a game?
No.
You don't have any games? What kind of birthday party is it?
It's a 1-year-old.
Are you bringing a broken glass? Because you love broken glass.
That's for snacks, Alex. That's called the recipe. Whoa. Ooh. No, this is good.
Objects at low temperatures often feel cold,
Okay,
while
start.
objects at
No, we
high
already heard the beginning.
the temperature of a substance or object is proportional to the kinetic energy of its atoms or molecules. Objects at low temperatures often feel cold, while objects at high temperatures often feel hot.
Wow.
Particles of an object at low temperatures have low average kinetic energy. Particles of an object at high temperatures have high average kinetic energy. When two objects with different temperatures are in physical contact, a transfer of energy occurs. Heat is the energy transferred between objects because of the difference in their temperature. The natural flow of energy is always from the hot to the cold object until both are at the same temperature.
What? But the marshmallow has not melted yet.
We have to keep watching till the marshmallow melts.
What kind of heat transfer is that? Conduction, yes.
What's your function?
Okay, so heat has units of joules. The heat units, joules, equivalent value, that's the SI unit we will be using. You can measure it in calories also, and it's equal to 4.186 joules, but we're going to use the joule. And it's equal to a kilogram times meters squared over second squared. Or really a Newton meter, right?
If we read all of our answer in calories, then we get it wrong.
Yes. No. You could. And what three ways can an internal energy be transferred from a hot object to a cold? So we know conduction is heat transfer through molecule-to-molecule contact, so they have to be touching each other. Metals are very good conductors, and styrofoam is a good insulator. Convection is the energy transferred by the movement of a fluid. A lot of times we talk about air, but it's also water. Hot air rises. So hot air in a room will rise and cold air moves in to replace it. Same with outside. Even outside on hot days, hot air rises, cold air sinks, which is why that's when the hot air all rises and the cold front is coming through. You get those huge thunder clouds because it's pushing all that hot air up. When we had our weather class in college, he said that the cold air is almost like a bulldozer coming through with a edge and just scooping up all that hot air and making it go up. The thunder clouds. What about a convection oven? Anyone have a convection oven in their house?
I do.
Yep.
It's a little fan that it spins.
Yep. The little fan blows the air around so it keeps an even heat.
The fan spins another fan.
Also, like in the ocean, the currents in the ocean, those are all based on hot and cold water. So it's movement of fluid. Which coast has the warm current? Do you guys know? Yep. West Coast has a warm current and the East Coast has a cold current right along the shore.
Because the water comes from different spots.
Right, they're moving in different directions. They're going this way. Yes. Radiation is the transfer of energy by electromagnetic waves. So no matter is actually transferred, only energy. So when you're standing by a campfire, you're feeling infrared. So we have, that's radiation. Same with the sun. The sun uses radiation transfer to get the heat to the earth. Let's see what she says about the... I know. That last one was very mind-blowing.
Oh, she closed the tab.
In the summer, a car parked in the sun can get extremely hot.
Wow.
This energy can be transferred to you as heat. Where does that energy come from, and how is it transferred to you?
The sun.
The radiation from the sun warms the car. This radiation consists of both visible and invisible wavelengths of light. When you first touch the door handle, it transfers a great deal of energy to your hand where you touch it. Energy transfer by touch is called conduction. Conduction is between two objects that are in contact with each other or within a single object. When you open the door, a black light warms your face. The very energy in fluid current. Energy transferred as heat is always transferred by one of these three methods: radiation, conduction, or convection.
Fire, what if he wants his wife to drive? No problem?
Hey.
He's got to clear the blood out first.
Okay, work can be done. Work can be changed into internal energy. So when you rub your hands together, you'll feel the increase in internal energy because of the friction. You're doing work, and it's causing friction, changing it to thermal energy. And when you pull a nail from a piece of wood, have you ever touched the nail right away?
Or like using a drill.
Or drill. Mm-hmm. And that's the friction there making that hot. So mechanical energy is potential plus kinetic energy is conserved when there's no friction, but these are all cases where there is friction. So the total energy, including internal energy, then is always conserved because you can change potential and kinetic energy then into thermal energy, which is included in the internal energy. So the change in potential plus the change in kinetic plus the change, remember U is internal energy, is equal to 0. So any loss of one type is balanced by gain in the other. So even if you lose all your potential and all your kinetic, you transferred all that energy into internal energy. Predict the sign plus, minus, or negative for the change in each quantity when. Okay, a child slides down a plastic playground slide. Would potential energy go up or down?
Down.
Kinetic energy would.
Oh.
And internal energy?
Amazing.
Hmm? Well, the child would have friction against the slide. Would make it warmer, slightly warmer, so it would be both. Yeah.
That makes a big difference.
A car applies the brakes to stop on a level road. It'd be the same thing, wouldn't it?
Yes.
Yeah.
Except the opposite.
Wait, doesn't it make the potential more?
Yeah, yeah.
Potential more? When you're.
The kinetic is decreased
Oh yeah, kinetic would be a decrease. Who's that?
The opposite.
Yeah.
Your internal state.
So your potential energy increases because you can hit the gas then,
Yeah. Well,
or you let off the brakes and it will still go because you have you're in drive. I guess that's true when you're in. If you're even like stopped at a stop sign, you have potential energy because once you release the brakes, it's going to go again. Right.
Does the car have tires?
Okay, I think we were all okay with those questions. Let's see. Let's go through a little bit of this. At least we'll see where we want to stop. What property of water makes it so useful as a coolant in automobiles, nuclear reactors, and other machinery?
oxygen.
Abundant.
Okay. Can take.
It can absorb a lot of energy. Yes, it can absorb a lot of energy without changing the temperature much. Has a high specific heat. Yeah, like the ocean. Like Sam's water bottle this morning.
Yeah. No. Me and Miss Clay hung out.
How does it differ from other liquids regarding its ability to cool? It's very, compared to its similar molecules, it has a very high freezing and boiling point. So it's not going to. You could turn to ice? What?
No, it was nice.
Oh.
What? You have lights. Yeah.
So what do you feel, why do you feel cool when getting out of a warm swimming pool on a hot day? Have you ever been, it's heat of the summer, the wind, and what's the wind doing?
Drying you off.
So the water is evaporating and it has to take energy from somewhere. Where does it take energy from?
Your body.
Your body. So it's taking energy when it's pulling energy from your body, it makes it feel cold. so that's why you feel cool. Same with wind. There's a little air buffer basically around your skin that's about the same temperature, but when the wind is going by, it's making those molecules move away, and so it makes it feel a lot cooler. And that's why on a humid day it feels even hotter, because your body is trying to evaporate or sweat, but there's so much water in the air that not much water can get into the air, and so it makes it's not able to evaporate and cool yourself off. Hmm. Okay, specific heat capacity, we use a little c. Measures the amount of heat required to raise the temperature by 1 degree for 1 kilogram of that substance. So every substance has a different specific heat. So it's how much energy is required to raise the temperature by 1 degree Celsius for 1 kilogram. Last year, I know honors chemistry, I think. Well, I guess I take that back. Mr. Morris was teaching. I can't remember exactly. We usually. Actually, I think I usually write it this way. So if you remember this one, it's the same. It's just rearranged for this is specific heat. Some books you'll see C is written as S, but it's the same. The units for specific heat is joules per kilogram degrees Celsius. Oh, here we go. Oh, they have cm. I like MC. However you want to do it. This is the specific heat capacity. It's table 4 from your book. Yep, memorize it. Suppose each metal shown above absorbs 10 joules of energy. Which will show the greatest increase of temperature? Are you looking for the highest or lowest? Lowest, right. You want to look for the lowest. Lead. Looks like lead, yep. Because it doesn't take as much energy to raise it 1 degree. How does water compare with iron? Look at water. Water is 4.186 times 10 to the third, compared to iron 4.48 times 10 to the second.
Water's the best.
So it takes a lot more energy to raise that water a degree, which is why people who live by the ocean have more moderate temperatures climate, because the water, that big bodies of water are able to moderate the temperature around them. Because I think it's San Diego. I think San Diego and Nebraska are pretty much on the same latitude. And so we should have we're the same distance away from the equator, but because they're by the ocean, it's a lot warmer. The average stays around 70 the whole year.
That's not very nice.
No. When you turn on the hot water to wash dishes, the water pipes have to heat up. How much heat is absorbed by copper water pipes with a mass of 2.3 kilograms when its temperature is raised from 20 degrees Celsius to 80 degrees Celsius?
100.
Okay, so we have,
QMCAT.
oops, you can't see black on there. So we're looking at heat, so that is Q. The mass is 2.3. Ooh, what's C?
4.138 inches.
But it's a copper water pipe.
Dang it, I was just going.
How much heat is absorbed by the water pipe? So copper is
387.
Delta T?
Change in time or temperature?
Temperature. Actually, I bet they have it big T, don't they? What do the units?
Well, kilogram, cancel.
So we need degrees Celsius to cancel. So it's not seconds, it's in degrees Celsius. And what is that?
I'll do it on it. I'll do it. Come on, Alex. Derek Miller was a drink. He had done that.
He would have it done. I mess with those guys. I got
Buddy, that's better.
3, 4 of what?
You better.
To the 4?
Think about it. You got it. There you go.
I'm gonna write it on that for the end of the year. I'm gonna hope for that crazy. I'm gonna hope for that.
There you go. Whoa. Can't read the bottom one. The cooling system of a car engine contains 20 liters of water.
Oh, geez.
What is the change in temperature of the water if the engine operates until 836 kilojoules of heat is added?
Okay, so 836,000.
Nah. You have to change that to joules.
Equals 20 times x times 4138.
Oh, X is, we're looking for change in temperature.
Why did you write scientific notation? No one even
Does that
likes
bother you?
scientific- Look at that first one, 836,000. How would I understand in scientific notation?
4138?
Yeah.
Mhm.
But I always write
Yeah, but she still has 4.1. All they do is raise that one.
do something special. You write
Okay, Shamira, do the math.
Okay, our change in temperature is
Schwann degree.
14.
Jacob, do you understand?
I'm paying 10.1.
10,000 Celsius.
you don't understand? What part don't you understand?
I got lost on the heat transfer.
We're just use
I got
both.
convection and I didn't even know it's Q.
Okay, Q MCAT. You know what the MCAT is? The MCAT is the test you take to get into the medical school.
Q. There are questions.
I'm not
on
kidding.
that.
It is.
Questions are
So all that's doing is we're taking the equation Q MCAT.
equals mass times calcium.
No. Specific heat, which is that constant that was on that table.
So you'll be given the C value.
It wouldn't even be calcium, it would be carbon.
Okay, you'll get the C value, and then what's the last one?
Change in time. Temperature.
There you go.
There you go. I knew everything.
Yeah. Okay, suppose that it's winter and the car's cooling system is filled with methanol. The density of methanol is 0.8 grams per centimeter cubed. What would be the increase in temperature of the methanol if it absorbed 836 kilojoules of heat?
Well, we have to change that to kilograms per liter.
But we don't have anything with meters. Let's see. I can't read what's on the. Hold on. Let me.
Let's just skip it. Ooh, nice catch, Gary.
Dang it, Curtis.
What?
You missed. You missed.
Okay, we're using the information from above too because how much methanol would be in there? If it can hold 20 liters of water, how much methanol would it hold? 20 liters.
1 milliliter equals 7 liters.
Okay, so let's go 0.8 grams per centimeter cubed. We said, Alex just said 1 centimeter cubed is equal to 1 milliliter. And then we can say there's 1,000 milliliters in a liter. But then we also need 1,000 grams in 1 kilogram, right?
You know a centimeter cube equals 9,000 cc equals milliliter.
Yeah, when you hear cc's, like
Basic stuff.
in a syringe. Maybe he uses syringes a lot. So let's cancel out some stuff. Centimeters cancel, milliliters cancel, liters cancel. No, liters don't cancel. We're left with liters. Grams cancel. So we're left with kilograms per liter, and then 1,000 cancels. So what's our answer? 0.8 kilograms per liter. Same. So now, if we know it has 20 liters, we need to find, we can use this to find mass.
You're better than us.
So what's the mass?
1
16.
It should be 16.
Yeah, 16.
High five for Matt.
That's 5 for America.
Okay, so Q, what would be the increase in temperature?
Well, put the 836
Yeah.
000.
I'm going to put it up here even though it's the other problem.
Equals 16 times.
Ooh, methanol.
Go back to methanol.
Is it on there?
No.
Oh, no.
Oh, wait, I think I know this one. It's 0.
No. I don't know what methanols is.
Uh-oh.
It's times 0. Methanol is 0.
Let's just put methanol.
Just put met.
I was going to, and then I was like, oh, better not do that.
The specific heat of met.
And then you would solve for delta T. We know how to do it. We just would have to look up the methanol's specific heat. Okay. Do you want to do another one?
I think that's
No, I think we understand the concept, which is only been right.
Yeah.
should call it a day.
Calorimetry. I know you like. No! No!
Would you rather have these problems or those study guide problems?
Physics problems! Yay! Yay, physics problems! The ones where you get the crazy answers, the impossible answers.
Like the worksheet?
Yeah.
No.
Keep these. We like these.
Oh, okay.
Yay, R59.
Ooh.
Yes, this is good. I like these. I learned.
Yes, these are awesome. Wait, what was yesterday's?
Alex, keep your shirt on.
What?
Alex, that's inappropriate for school. No, do not approach me, Alex. No, this is wrong.
You just lost
Stop.
your participation payment.
Stop. Alex, no.